I split this unit into two units, two parts of it. The first part is just going to be reviewing how to do oxidation numbers and how to balance redox reactions using the half reaction method. And then the last half of the unit will have to do with batteries and all the other fun stuff that we get to do in electrochemistry. The most applicable part of electrochemistry are batteries, and that is where electrical energy is stored as chemical energy. Batteries are based on redox reactions, and if you remember, reduction is the gain of electrons, oxidation is the loss of electrons. I like to remember it with oil rig. Oxidation is loss of electrons, reduction is gain. Some other teachers like to use Leo Ger, loss of electrons is oxidation. Ger, gain of electrons is reduction. I just think oil rig is easier. And electrochemistry is just the study of the relationships between electricity and chemical reactions. How do you know if a reaction is a redox? Well, you have to look at the oxidation states in the reactants versus the products. And if they change, you have a redox reaction. So remember that oxidation number is not necessarily the charge on the periodic table. Now, some things usually get their charge from the periodic table. Oxygen, the really electronegative ones do, the first column, sodium, etc. Almost always a +1. It's just a few that are different. But here are the rules briefly. Please consult your textbook or online for all of the rules. But if you look at an element and it is in its elemental state, it has a charge of 0. What do I mean by that? If it just says magnesium solid, that's how magnesium occurs in nature. It has a charge of 0. O2, oxygen gas, that's how it occurs in nature. It has a charge of 0. H2 has a charge of 0. But if you look at that example in water, they're together. Well, you know if things come together that there's going to be positives and negatives going on. Well, in this case, O is the more electronegative, so it gets the charge from the periodic table, a -2, which means the other side has to be a +2, but each hydrogen is going to be a 1. So, and we'll go over this on a POGL. We'll review how to do all these, and we pick it up pretty quick. Just remember, one of the easiest ways to spot a redox reaction is if you have something all alone, like O2, and on the other side it has a partner, guaranteed it's redox. If you just see Cu sitting all by itself, and over here it's CuSO4, it's going to be a redox. And then two other words that we don't really deal with a whole lot in regular chemistry, but the oxidizing agent and the reducing agent. Kind of weird. Go with me on this. The oxidizing agent is the one that is reduced. What it means is that it is causing something else to be oxidized. The oxidizing agent is oxidizing something. It's forcing something to give up its electrons so it can take it. The reducing agent makes something else be reduced. So it's making something take its electrons. So the reducing agent is actually being oxidized, and the oxidizing agent is being reduced. I know, it seems weird. Like I said, we will review how to do oxidation numbers together in depth, and seriously, after just one POGL, you'll have it down again. Then we're going to move into balancing redox equations. I always have some student who says, I don't have to do this method. Well, by all means, good luck. Let me know how it works out for you. You really, really need to do the half reaction method. It is a process. It does take a little bit of time, but you will get the right answer every time. And here's what's tricky about them. Not only do you have to keep track of the elements on both sides, like we always have, we also have to keep track of the electrons. And that's where it gets tricky. If you don't do the process, you're going to mess this part up. Just remember that electrons are neither created nor destroyed. And we're going to see that in redox reactions, when we use the half reaction method, you have to have the same number of electrons in both half reactions. And what do I mean by half reaction? That simply means that we're going to take an equation and we're going to split it up. We're going to look at the thing that's being oxidized and the thing that's being reduced. We're going to balance each one on its own. And then before we add them up to get the overall reaction, we'll make sure our electrons balance, and then we'll just add them up. And sometimes there's a little bit of algebra, like combining like terms. Oh, there's H's on this side, and there's H's on this side. Bring them together. Or waters often have to be combined. So there's a little bit of algebra, but it's not that bad. So let's take a look at an example. So there is the full equation. A tin ion plus iron ion making a different tin ion and a different iron ion. So what you want to do first is just split them up. And you don't even have to know who's being oxidized and who's being reduced. All you need to know is that I bet the SN2 plus goes with the SN4 plus. And I bet the Fe3 plus goes with the Fe2 plus. Now, where did those electrons come from? Well, if you look originally, if you just put SN2 plus down and SN4 plus, yeah, the tins are balanced, but the charge is not. You've got a 2 plus and a 4 plus. You need to make those charges be the same value. And the only way you can do that is by adding electrons. So take the number that's more positive and bring it down by adding electrons. So in tin, if you add 2 electrons, you make that whole side have a 2 plus charge. And then it's kind of the same thing with the iron. You've got the 2 irons on both sides, so they balance out. But on the one side, you've got a greater charge than the other, and we just have to add some electrons. So pay attention to where you add those electrons. When you have the half reactions, one reaction is going to have those electrons as products. One's going to have them as reactants. If they're both showing up on the same side, you're not doing something right. And just think about what it means. If you have electrons as products, you're getting rid of them. You're giving them away. That's oxidation because you're losing the electrons. If the electrons are reactants, it's because you're adding them on, you're gaining them. So we'll walk through quite a few of these in class together, and I really like them. I think they're a lot of fun. There's a process. Once you have that process down, it's pretty easy. And I find most students who've done this in regular chemistry and come and do this in AP or college chemistry, it comes right back to them. It's like riding a bike. This would be a good slide to pause and write down how to balance a half reaction. Now, there are other methods online. I personally find this one to be the easiest. Now, these are the rules for balancing redox in an acidic solution. So first, again, split them into 2 equations. And even if you don't know which one right now is oxidation, which one's reduction, you'll get there pretty quickly. And then the first thing you do is you balance all the elements that are not H's and O's. Then you balance O's. And a lot of times you do that by simply adding the number of waters you need. So if you need 4 oxygens, you add 4 waters. Now you've got a problem with hydrogens, so now you balance by adding hydrogen ions. And that's okay because this is an acidic solution and hydrogen ions are acidic. And then the last thing you want to do is balance out the charge by adding electrons. I always forget that step, so don't do that. And then once you have both half reactions balanced, and I usually do one at a time, you can't add them together unless the electrons cancel off. So this might require you to multiply an entire equation through by 2 or 5 or something like that. And then again, in the very end, just make sure you've combined like terms. If you've got hydrogens on both sides, combine them onto the one. If you've got water on both sides, combine them onto the one side. And you should, in the end, be able to look at that final equation and you should see that all of the atoms balance and you should see that the charge balance as well. Let's go ahead and glance at a problem. And I've got it already worked out, so if you want to stop and pause and kind of work it out along the way, great idea. But there's the overall equation. So the first thing you want to do is break it into the 2 half reactions. We know the thing that has manganese needs to go with the manganese. We know that the C has to go with the C. So split them up like that. The next thing you want to do is balance everything other than H's and O's. Now, I usually do one equation all the way through at a time, but for the sake of the slides, I'm doing them both together. So you'll notice in the Mn equation, the Mn's are fine, but you need to fix the O's, and then which we'll do in a moment. And the other equation, well, the C's don't balance. So we first start by putting a 2 in front of the CO2, and that takes care of the carbons. Again, the Mn's balanced out, so we didn't need to do anything yet. So now that we've balanced everything other than H and O, tackle the O's. And you do that by simply adding water. Well, in the Mn equation, you've got O's on one side, but none on the other. Well, mass isn't created or destroyed, so just slap some waters on there. Now, we don't need to do that with the second equation because by putting the 2 in front of CO2, we took care of both the C's and the O's. So this one's a little bit easier. Now you'll notice with that first equation, oh no, you just added H's. What do I do now? You just add hydrogen ions to the other side. It's not a big deal. We're in an acidic solution, so adding H's is totally acceptable because H's are acidic. Now we've got all of the atoms balanced. The last thing we need to take care of are the electrons. So the last thing we need to do now is to fix the charge. And if you look at that first equation, and this does get tricky for students, but you have 8 H pluses. That's a plus 8. MnO4 negative. Well, 7 minus 1 is a positive 7. So on the reactant side, it's a plus 7. On the other side, the only thing that has a charge is that Mn, which is a 2 plus. So you've got a charge of 7 and a charge of 2. We need to make them be the same number. Take the one that's higher, more positive, add electrons to bring it down. So by adding 5 electrons to that side, we make this 7 go down to a 2. And then notice the other one, you've got negative 2 on the one side and nothing on the other. So take the other side, which is 0, and add 2 negatives to bring it down. So now we've got completely balanced half reactions. The next thing you want to do is you want to look at the 2 equations. Can we add them up? Unfortunately, we cannot. The first equation has 5 electrons and the second one has 2. The electrons must balance. So if you multiply the entire first equation by 2, that means you multiply everything. It's the distributive property in math. And if you multiply the entire second equation through by 5, now your electrons will cross off. And then simply add them up. And this doesn't look to be one of them, but sometimes you'll have H's on both sides or waters on both sides, and you'll want to combine like terms. This does happen in acidic solution, but it's most notable in a basic solution. And just for the record, on the last slide when I was explaining about adding the electrons, suddenly there was this little bubble that came out away from my head with a thumbs up sign. I have no idea how that happened. I'm going to go with AI of some kind. Anyway, balancing basic solutions. Now, there is a totally different method that you can do for this. And I've looked at it, and quite honestly, I just think it's more difficult. I think it's easier to go with the same process you've just learned and add one more step. That's my recommendation. But feel free to go look up the other one and try to figure it out on your own. Here's my recommendation. When it's in basic solution, follow the same process you just followed for acidic solution. Here's the problem. Now you've got an equation or two that have hydrogen ions just sitting there. That's acid. We can't have that. So let's say you added 8 hydrogen ions. What do? You add that same number of OH ions to both sides. So on the one side where you already have the 8H, when you add the 8OH, you just make water. In fact, combine those together and actually rewrite it as 8H2O. Then on the other side, you have the OHs. See? Basic solution. Now, this method does have an extra step. There does tend to be a little bit more algebra. You tend to have to combine like terms a little bit more. So just pay attention to that and be careful. And again, in the very end, look at your overall equation. Do your atoms balance? Do your charge balance? And if those all balance, then you did it correctly. The next video gets all into batteries and electrochemical cell potential and all sorts of cool fun things. But before we jumped into that, I just wanted to clarify one thing. There are 2 types of electrochemical cells. One are called galvanic or voltaic cells. Okay, these are batteries. These are spontaneous chemical reactions that provide us with electrical energy. And you're going to have a metal in its solution, a metal in its solution, a salt bridge, and a wire connecting them. That is what we are going to deal with. There is something called an electrolytic cell. Now, this is where you have to use an outside electrical energy source to make a non-spontaneous reaction go. So while galvanic or voltaic cells are batteries, electrolytic cells need a battery. And there's your difference.